Good afternoon. I'm Jerel Unruh, and I work at Toyota Connected, which is a new technology offshoot of Toyota. And there's about 16 of us here this weekend, I think, from Toyota Connected. And there we're on the mobility services team, and we're tasked with building car sharing, fleet management, ride sharing, and some other things. We have a partner in Hawaii named Servco that's currently using our product, and they're using it to rent out vehicles. And you can reserve a vehicle from a mobile app, iOS or Android, and you can show up, unlock the car, get in, start it, drive off, and when you're done with your reservation, you can return it, all from the mobile app with no physical key. And that's all backed by an Elixir cluster on the server side, and we really enjoy using Elixir. So in this talk today, this is what I'm going to try to cover. Talk about architecture a little bit, the way we're used to architecting web applications, and then how we do it with Elixir. And then we'll go into registries a bit and end up with Swarm, and then talk a little bit about managing state in Gen servers. So a lot of us came from a background where we wrote applications with Rails or Django or PHP or various types of frameworks like that. And the style typically is you start off with a single node and a database of some sort. And for the purpose of this talk, I'm just referring to it as Postgres, but it could be any sort of long-term storage. And then when you start to scale it up, you might start adding nodes, and you have things you want to do in the background, and maybe that's sending emails or something that you don't want the user to have to wait on. So then you would spin up worker nodes, and then you would connect them with a queue, and so your web nodes would push things on the queue, and your workers would pop things off and save some state to Postgres when it was done, and so on. With Elixir, we start off the same way. Most projects do. You have a node and a database. And then things start to get a little bit different. You have background things that you want to do, like sending an email when somebody resets their password. And rather than having to have a queue and worker nodes and so on, you can just do that in a process without making the user wait for it. And then when you start scaling up, you have multiple nodes, and you can connect those together, and now you have a cluster. And that's pretty much it. You're not forced to have worker nodes in a queue and so forth. So let's talk about these processes just a little bit. By default, a process, if you just spawn it, it'll have a PID, process identifier. But you can also, like you see on the right there, you can also name it with a static name. You can give it an atom, and then you can refer to it through that name anywhere on that local node. And in this example, I have something named vehicles, which you'll notice I use the vehicle example quite a bit, which I guess is appropriate since we're a car company. But I have this process named vehicles, and maybe it holds a map. And in that process, in that map, you could have a number of vehicles stored, and you could pluck one out by its key. Maybe that key would be the VIN or primary key in your database, but if you want to know something about a car, you could send it a message, and then that Gen server could pick that thing out and return it. But that would end up being a bottleneck. Every request for any vehicle would end up going through that one process. So it'd be nice if we could go this route, where we have a process for each thing that we care about, maybe a process for each vehicle. And if you could have it named by whatever that identifier is, the VIN or the primary key, that would be great. Well, we can do that. We can use the Elixir registry, and that was merged in Elixir 1.4. And using the registry, which is local only, on a local node, you can save a reference to a process by some name. Maybe it's a string or so on, a binary, that you want to look that process up by later. And whenever you call registry lookup, you'll get a PID back and any meta information that you saved along with it. So then you end up looking like this. You've got this on every node, and it works great. Maybe you have a write-through cache or something, and that's fine. So you see we've got processes identified by VINs. So you've got VIN1 on every node. And that's good, but what if we could get to this? We've got the green, which represents worker nodes, or worker processes, worker processes running and doing things, and then we've got yellow, which identifies stateful processes. So rather than having this duplicated and getting out of sync, perhaps you could have a process on every node, just once in the cluster. So the load is spread across the cluster, but they're unique. And we can do this using distributed process registries. And there's a number of these. Each of them have different strengths and different trade-offs. And I've not used all of these, but there's Global, gproc, PG2, CPG, SYN, Swarm, and probably some others that I missed. And I'm going to talk, well, first, when you use one of these, this is roughly the architecture you can end up with. You can have a unique process across your cluster. I'm going to talk about Swarm for the next bit here. And to get this, instead of spawning a module directly, you can replace that with Swarm register name. And first you give it the name that you want to always refer to that process with, and then you give it MFA, or module function arguments. And then Swarm will take care of spawning that process, and it will track changes in your topology. So if you have a node go down or something, Swarm can move that, restart it on a different node. So let's talk just a little bit about some of the properties of Swarm. First off, out of the box, it is AP. If you're used to thinking about the CAP theorem, it values availability even when partitioned, and it's eventually consistent. So something that happens on one node won't magically happen in the same instant on another node, but it will synchronize very quickly to the other nodes in the cluster. And it uses consistent hashing to decide which nodes your processes run on. Now, if you would think about it, just a hash table, if you had 2,000 keys spread across 100 locations, or let's just say 100 nodes, you would need to move 1,800 keys across 99 locations if one node with 20 keys went down. So with consistent hashing, it works much, much better for dynamic cluster sizes. If you have nodes that join the cluster or leave the cluster, for the same example, if you had 2,000 keys across 100 nodes, you would only need to move 20 keys if one node with 20 keys went down. So it's much more efficient for that type of setup where you have dynamic sizes. The Swarm registry is held in ETS, so a lookup for a PID to reference what a name, the lookup for a name is very, very quick in ETS. And it supports process groups. So you can join a process to a group, and then you can broadcast or call everything in that group. And like I mentioned, with consistent hashing, the dynamic node membership is a strong point. So there's an optional dependency called libcluster that you can also install. And this example here is for Kubernetes. And what it does is it uses the Kubernetes API to get information about what Kubernetes knows is running. So if you bring up another pod in Kubernetes, libcluster can fetch the IP address for that new pod and connect that to the existing Erlang cluster. And there's also support for the Erlang distribution for Rancher, and you can do custom topologies with libcluster. So I mentioned earlier about using swarm register name, that if a node went down, Swarm could restart processes on a different node. So let's look at how that works just a bit. Let's say that we have a node that crashes, or we take it down. Swarm will take the processes that were assigned to that node's key space, and it will restart them on the other nodes. And then if we bring that node back up, it can move those processes back to that node and then kill off the extras. And perhaps second node goes down, it will keep doing that process. And you could possibly use this for rolling deploys. As each node in the cluster cycles, Swarm can restart processes on other nodes. So let's look at what that looks like from the processes perspective briefly. If you're going to have a process that's managed by Swarm, you need to add some callbacks. And we'll go through them right quick and look at what each one of them does. The top one is basically just a shutdown hook. Before that process gets killed, you can do any sort of cleanup that you would need to do. The second one is called before a process potentially is moved to a new node. So in the previous example where you have nodes going down and coming back up in your cluster, Swarm can call this process and say, hey, how do you want me to get a representation of you on the other node? And you can either return restart, in which case Swarm would start a fresh process on the other node, or you could return ignore, which would just leave you running where you're at right now, or you can return a tuple, resume, and the state. And if you do that, Swarm will then take that state and move it across the cluster, and that's where the third callback comes in, and that's end handoff. It will give the brand new process that just barely started up, it will give it the state from the old process, and you can then return it in your no reply tuple to begin running with that state. And the last one is in the case of a split brain scenario where your cluster is divided. When that heals, Swarm will kill off any duplicates, and it will call this callback with the other state. And then it's up to you to figure out how to choose between the two states that you have. So let's look at a quick demo here. What we have here is the very top is just a debug node that's just tallying the count of all running processes. And then the bottom three are running identical code. So we'll start node A, and then we'll start the one at the top that tallies the running processes. And you should see each node show up there and a total of the processes. So what we're doing is spawning 500 processes named 1 through 500. So no matter what happens to this cluster, there should always be a total of 500 running, and they should be roughly spread across nodes A, B, and C. So now we have C started. You see the total changes briefly while everything synchronizes, but then we're quickly back at 500. So let's kill node B, and you see we're still at 500. Quickly restarted those to replace. And let's start B again. And we're still at 500. And let's kill C. So we just go through these, cycling the different nodes. And the load should be roughly equal. I think there's a test in Swarm that's, should it assert it to be about within 5% load across all the nodes. I'm using a very small number of processes here, but and looks like that's the end of the screencast. So what are a few things that we can do with a distributed process registry? If we have this capability of having a unique thing across the cluster, there's a few interesting use cases. And in this case, if we want to debounce something, let's say we only want some sort of work to happen one time in the cluster every 10 seconds, is what this example shows. We could call debounce.alive, and what it does is do a swarm lookup to see if we have a process with that name running. And if it returns undefined, we start a process. And if it returns one that is running, we return true. So then we know that this thing has already happened within this, in the last 10 seconds. And then in the init callback, we register ourselves with swarm under that name. And we set a timeout for 10 seconds. And so if, when that 10 seconds passes, this process will shut itself down. So there's a little caveat with this, and that is whenever you work with an eventually consistent, highly available thing like Swarm, there is always a potential for your cluster to be divided. So if you're wanting, you know, absolutely once per cluster sort of thing, you'll want to lean on your database or a tool like that to make sure. But for a lot of things we do, you know, debouncing a thing across the cluster could be useful. Another thing we could do here is, let's say that we have a stream of messages that are coming into our cluster, and one particular message isn't terribly important as long as we get the next one. So in that case, we could just spawn a process by that name if it doesn't exist, or if it does exist, we send it a message. This function is not in Swarm yet. I think there's a pull request open for it, but you can easily combine Swarm whereis name and Swarm register name to get the same functionality. But what we do here is we call this, and we're going to get a PID back regardless. If the process was already running, we'll get the existing PID. If the process was not running, we'll spawn a process and return that PID. So the last bit of this talk, I'm going to talk about Gen State Machine. I found it to be rather useful for managing, for sure, complex states where we would typically use a Gen server. And I'm going to make the argument that if you find yourself doing lots of timers, sending a timer to your own process, canceling that timer again, perhaps forgetting to cancel it, having a thing happen twice because you forgot, Gen State Machine might help ease some of that. So first off, we're used to talking about state all the time in a Gen server. And when you're working with Gen State Machine, what you would typically think of as state in the Gen server, we now refer to as data. It's just kind of a convention that I've seen. That's because since it's a finite state machine, you have state machine state, and the map or list or whatever that would be your Gen server state is best to be referred to as data for a variable name. So just pretend that an example you see with Gen State Machine is actually a handle call with the variable data in the last position. So to make sure we're all on the same page, there's just a quick diagram I threw together that roughly shows a Gen server. Every Gen server is going to begin in the starting state, and then the init callback will be called, and then it will be in the running state. And it will stay in that running state until it either crashes, at which point the supervisor will start it again, so it's in the starting state, transitions to running. It will do that until the supervisor gives up and propagates the error upward, or it gets a stop event, which moves it to the stop state. So we need to plan for failure when we're designing our Elixir applications. And what this might look like is if we have a vehicle process running, any sort of process that holds long-running state, there's parts of that state that have to do with how the process is running, and then there's parts of it that we really care about. Maybe we're doing calculations all the time, and we wouldn't want to save each and everything to the database, but there are some important things that we derive from that process that we do want to save. And so if we save that to our long-term storage, and our process crashes, when it comes back up, it can read that state from the database again and work out where it needs to pick up from where it was last. And so in a state machine diagram, it might look a bit like this. We started off with the same sort of thing as a regular gen server, but now we have this timer that causes it to transition to a saving event, or a saving state. And when it's in that saving state, it synchronizes with long-term storage, the things it cares about, and then it transitions back to a running state. And it will just stay, it'll keep doing that for as long as it keeps running. So let's talk a little bit about what that might look like. In this example, we're using Dynamic Supervisor to spawn a large list of child processes. And you'll notice what we're doing is we're using the child spec of the module and passing in just the primary key from our database. And we then spawn the process and get the PID, and immediately we make a call to that process with the whole record. And the reason we do that is because if we would pass in the whole record, then for as long as that process ran, that record would be frozen in the supervisor. And so if that process crashed and came back up, sure, it would get the record handed to it in start link, but that record would be stale. You know, perhaps other queries have updated the database numerous times, and then this process crashes and respawns, and suddenly it has this record that's possibly hours old. But if we would simply pass in the ID only and let the process query the database on its own, if we spawn a bunch of them, we would end up just DDoSing our database. So using Gen State Machine, we can have a fairly clean way of handling both of these cases. So we start off by using Gen State Machine, and in the init callback, we return an action that says, set this timer for 10 milliseconds from now, but if the state changes in between now and then, just disregard. I don't care about it. So state timeout is good only until the next state change. And then on the second to last line there, we return a tuple with 4 elements, and the second one, the first one, okay, is like any gen server. The second one is the state that the Gen State Machine starts in, which is starting. And then the third one is data, what we typically think of as a Gen server state. And the last one is the actions that Gen State Machine should play, which in this case is just the timeout. Forgot about my neat little arrow animations here. So on the next slide here, let's look at handling these. First off, we handled the call, which is basically just a gen server handle call. And what we do on the next line is we say, okay, let's trigger an initialize event, and then secondly, let's reply to the caller. So we will end up at this line. So in the happy path that I showed first, where you spawn a list of processes, this is what's going to happen. You're going to hit the first callback handle event call, and then you'll end up at the initialize on the second to last line. But if this process would crash and restart, we would take this path instead. Because the process gets spawned with only the primary key from the database, then nothing happens in the process for 10 milliseconds, and then that timer drops, which calls this callback. So we're in the starting state, and the event that happens is respawn update, and so that matches this pattern. And so then we go in here and we query the database, we fetch the whole record, and if it's been deleted in the meantime, we get a nil back and we just shut down the process. But if we actually get the record back, we return that as the new data for this gen state machine, and then we transition to this. So no matter what path you come into this process with, you're going to end up at this line. And so you can do any sort of setup and figure out next steps for what you want your state machine to do. One little option that you can enable on gen state machine is state enter. And what that does is it, on this line, if we pass that to use, it will cause this callback to be called with every transition. Anytime the state machine transitions into a new state, it'll call this function. And so it's really handy for logging what's happening, or even saving that state to your long-term storage. And then if this process crashes halfway through its life cycle, you can figure out what its last state was, and you can start work from that point. And this is really, really handy for debugging. This logger info line, you can grep your logs for FSM and the primary key that you got a bug report on, and you can see it transitioned from state A to state B to state D to state M to state Z, or maybe you'll see a crash in between there. Makes it much easier to figure out what path things took. Another feature you can do is postpone. So in our previous example, where we're spawning a list of processes, let's imagine that you have a caller that wants to know what the state of that process is. And so it makes a call to it. But you see what we're matching on is the starting state. So if this process is still starting, we don't have anything to reply with, but that caller would really like to know. So we can return a postpone action. And what that will do is it'll put the message back in the queue, and so when the state changes, it will replay it. And so the caller will just be blocked until the state changes, at which point we would end up matching on the running state the next time that was replayed. And then we can reply to the caller and continue on with whatever we're doing. Of course, if that took more than 5 seconds, your caller would get a timeout. But there might be a case even where you want to set it to infinity and just have the caller wait until this state machine gets to this state. So a few other projects I'd like to call out. Microsoft Orleans is a .NET project. I don't know if any of you have happened onto that, but they use terms like silos to talk about nodes and grains for what we would call processes. And there's a project called Orleans, which is written in Erlang, that takes the same idea, and it uses the same sort of patterns as what I'm talking about, where it saves the grain state to a database, and if that grain crashes, it can restore it. Or if a node goes away, that grain can be reactivated. I believe that's what they call it. Instead of spawning, it's reactivated on a new node, and it can retrieve its state from storage. And LASP looks like an interesting project. I believe Orleans uses parts of it under the hood. So just a short recap, a few things here that I wanted to point out. Seems like gen state machine can be quite useful for clarifying complex logic. If you've got multiple timers shoved in a map and you're trying to remember to cancel some of them and start a new one and so on, Gen State Machine might be useful for that. And I found Swarm to be easy to use in a dynamic cluster. Right out of the box, it's quite pleasant, quite easy to use, and fits quite well with a Kubernetes type of deployment. And publish and multi-call, while projects like PG2 focus primarily on groups, Swarm focuses on unique registries, but it also does support groups. So if you have a process join a group, you can then send messages to every process in that group, and that process could do some sort of calculation or so on, and then return a message. Multi-call returns a list of all of the responses from the processes in that group. And I'm going to argue that you can leverage your database when you need consistency guarantees. So I feel like Swarm gives us a nice middle of the road where you can use it for things that are not super critical to be once and only once. So for example, billing somebody, you probably wouldn't want to use a eventually consistent system for that. That's where it's handy to use transactions, locks, and so on. Another thing might be doing work. Let's say you have some sort of a cron system running in your cluster that does things on a schedule. You could supervise that process or manage that process with Swarm. And whenever it begins to do jobs that are saved in your database, it can set a timestamp for, let's say, started at or began at. And any job that is looking for things to do in the database can run a query saying only select things where started at is nil. And so it's quite simple from that perspective to use your database to ensure that while we expect only one thing is running, if something happens to have a duplicate, then just exit or ignore it. And I'm going to argue that partitions will happen. The question is just when. I know it's easy to think that, well, I'm running bare metal servers that are connected with a fiber link and partitions won't happen to me, but it's a really good idea to just plan for that to happen. That's all I have. Thanks.